It's a pleasure to introduce our more general public speaker today, one of the several ones which we have in our program. It's Rainer Glaschick from the Heinz Nixdorf Museum in Paderborn in Germany, who will speak on materializations of universal Turing machines. Probably you all have seen the Turing machine which is on display downstairs. So we are unable to lift the case up in order to bring it up here because it needs a heavy machine. So I suggest that we all go after the talk downstairs and take a look at it, if this is wanted. Okay, but now, it's your
yes. Thank you for the opportunity to present this work here for you. My name is Rainer Glaschick, as you said, and you already said it. Okay, let's start immediately. Just one remark before. I will have the emphasis on the historical aspects. So you will hear a lot of how it was and so on, and not so much on the technical and scientific aspects. What I will talk first as a warm-up, something about Alan Turing in Germany. Then I will describe what Turing machines are. For many of this might be boring, but I needed to refer later on. Then I will talk about Hasenjäger's materializations, and finally I will ask whether this was fun or science, what he did with this machine. The answer I will leave to you. Well, Alan Turing was capable of, please?
It's cut off the side, just like. Can you resize it maybe?
Okay, listen to my talk. we have to fix it on the record. I could change the operating system, but I don't know.
It's not too bad.
Well, let's try it just.
Yeah, you can see it on there.
What?
You just make the screen smaller. It doesn't need to be so big. It doesn't have to be full screen.
Yes, I will try to make the screens full. Wow, that's not what I wanted. Oh, it should be. This operating system is cheating. That's fine. So I have to put it on the left side. Well. No, same procedure. Okay, I propose that we deal with it, and you listen to me, and then you will get everything. This is only distracting you. Alan Turing was well capable of reading German texts. For example, he received Neumann's Grundlagen der Quantendynamik as a prize from his school before he went to studies, in German, of course. And so I think he really has read Hilbert's Grundzüge der theoretischen Logik in German, and that's why the word Entscheidungsproblem went to the title of his paper. And obviously he dealt with German language with the enigma description in Bletchley Park. He was several times, at least exactly 4 times as far as we know, in Germany. The first one was with his father walking in the Black Forest, 1932. The second one was a bit more interesting. It was a bicycle tour from Cologne to Hanover, and according to Andrew Hodges, he was visiting someone in Göttingen. We don't know whom, because as far as we think, there was a problem with his PhD, and he had to ask him. While he was in Hanover, in Germany, the SR was eliminated, sometimes called Röhmputsch, which has insofar interest as Röhm was eliminated because he was homosexual. And there we have a certain relation.
Can we see the bit that's out off the screen?
Yeah, we don't know how to.
That's on a pivot, so.
No. That's a problem with my computer. If you should I try to fix it, then I will change the operating system. No. Okay. These were the first 2 were more or less his private visits. Then he was 2 times as an expert in Germany. 1945 to Inquiry on Secret Communications. Remember, that was just while he was building the Delilah speech scrambling system, or has just built them. I'm not so secure with the years. And 2 years later, to inquire the state of computing machines in Germany as an expert. And this was already the time when he had specified the A's. So he was there 2 times as an expert for realize. I mentioned Burg Feuerstein, where you've seen a picture of Burg Feuerstein. But very important is the relation to the town of Münster and the University of Münster in Germany. At the end of the screen, I will show you where it is. The interesting thing was Turing's article on computable numbers with an application to the Entscheidungsproblem was a really breakthrough. We know it now today. So, and if you are young and you are publishing such an article, you expect a good reaction. At that time, there were no photocopiers. So the only thing to get a copy of the article was to write a postcard to the author and ask him for a reprint. And Turing got exactly 2 requests. One from Cambridge and one from Münster in Germany. So he was absolutely disappointed with the renowned. This came from Heinrich Scholz, who was just establishing mathematical logic in Münster in the Faculty of Philosophy, by the way, and had his article discussed in a seminar. His student Hans Hermes has published already 1937 an article in German, which I found these days, which gave some information, but not the full information what was in his article, was in Turing's article. And last not least, Turing was invited from 1952 on several times to come to Germany. Sometimes this was forbidden, then it was said that he was ill. I think it was, I don't know why, but it wasn't possible that he came to Münster. The people in Münster did very look for him in his work. There you see where Münster is in Germany, here in the middle of Germany, and there approximately is Paderborn, there's Hannover, Bremen, Hamburg, Ruhrgebiet, and so on. So that you just have an idea where this university is. Hans Hermes had the student of and leader who followed Scholz, had published 4 articles about the Turing machine, and finally a book, Aufzählbarkeit, Entscheidbarkeit, Berechenbarkeit, enumerability, decidability, computability, in which a Turing machine had a central role. So the influence was there. Then we had 2 students of Hans Hermes, Gisbert Hasenjäger, that is exactly the Hasenjäger of whose machine we are talking about, and Dieter Rödding. They had a Turing room in Münster, where they had collected the machines, the reprints, and everything else. I don't know exactly what was there, because this was very early when Dieter Rödding died, early. Didn't no longer exist. And the funny thing that came out now in this preparations for the expositions and books and articles was that Hasenjäger was Alan Turing's counterpart for the security of the Enigma. The Germans had 1 person, Hasenjäger, and 2 persons for the other decryption system that should try to look for bugs. He said he had no idea, and the Germans had really no idea, that Britain would put so much power in the decrypting on the other hand. He found some minor weaknesses, but not the real ones. And he said that was good, because otherwise a war would have lasted longer. There we see Mr. Hasenjäger with an Enigma machine. Just before I come to Turing machines, well, it has often been said that Turing was ahead of his time, but I would like to repeat this. in 1963 with his article on computable numbers. He had a programmable machine that solves the Entscheidungsproblem, but that was not all. In 46 he specifies a high-speed universal computer. From my point of view, for years, until mid of 50s at least, the world's fastest and powerful machine, never recognized as such until these years now. In 1949 he had an article about how to write software reliable, how to make software in a way that you can verify it, the first beginnings of it, but still ahead of our time, because nowadays, from my point of view, this has not yet been finished, this work. And in 1950, can computers think? So he was far of his time ahead. Now I'm going to explain to you the Turing machine, for those of you who don't know how it works. We have at the top an infinite tape, which has fields, and on the fields there can be markings, and there's a read-write head, then we have here the state table that has here the state number, the input symbol, the action that to be done, and the new state number. And this is a final state machine, as we say, and it works. For example, this example, I will use it later on, works as such. If the tape is marked, go to write, then this moves over to write, stay in state 1. If the tape is not marked, for example, because it has advanced here, do nothing but change the tape state to state 2. In state 2, if there is nothing on the tape, it was occupancy the tape, then mark the tape, stay in state 2, and in state 2, if you see a marker, which is now there, do nothing, stay in stage 2, so that means the machine stops insofar as it does nothing more significantly. Well, with this stop instruction, you see the differences between computer scientists and mathematicians. Mathematicians say, okay, we simply drop the last line. When there is nothing more to do, the machine stops. The computer expert would like to have a stop instruction instead of doing nothing. What does this? It adds a marker on the end, and we are using the so-called unary representation for numbers, so it adds 1 to a number. Now I will go to show you this in a short video that you can easily find in the web. Where is it? A Turing machine. I think this one. The interesting thing we can see, there has someone tried to build a Turing machine as accurate as possible, and you will see it writes zeros and ones, and just a look and erases stuff there. This is really nice, this machine. Just look in the web for video of video and Turing machine, and you will find this. Now Turing has used this machine to define computability. He has an A machine from automatic name, not from A as the first in the alphabet. Machine calculated the value of a function. That was on computing numbers. I want to compute, he said, the value of a function, the numerical value of a function, as a real number in binary decimal notation, the fractional part. And thus, computable numbers in the original Turing sense, I'm talking about history, are those that were produced by cycle-free machines that produce this digit endlessly, because many numbers are not rational, so we have an endless, non-repeating number of digits. This has changed within the science up to now, but this was the original. And he used alternate fields for the result and the working space. The idea of Turing behind this was, he said, I have an abstract idea of someone working on a piece of paper. And he has a scratch pad and he has the final results. And by the way, erasing was only permitted on the scratch pad. So many of these nice Turing programs nowadays that add two numbers by putting a 1 between and erasing the end some 1 on the end, and not what Turing wanted. This does not say something about the value nowadays. And the result was called a computable sequence. And now, what's Turing's trick? Look at this state table. I can encode it easily as a number. The state numbers in states 1 and 2 are clear. These are 1 and 2. I use 3 for M, R for 4 for right, and 0 for nothing. Then I have this 16 entries there, and they give exactly these numbers. So my Turing machine is now converted to a number. As his machine was on computable numbers, that is, compute functions of numbers, he could apply his machine to these numbers. That, from my point of view, was a real trick that he did. And the main result I cite from his paper, a number with a description number of a circle-free machine will be called a satisfactory number. And then in paragraph 8, he shows that there can be no general process for determining whether a given number is satisfactory or not. And that was the result, that there are things that cannot be solved. And then he applies it to the Entscheidungsproblem. And I have to read it. The results of paragraph 8 have some important applications. In particular, they can be used to show that the Hilbert's Entscheidungsproblem can have no solution. I show here there can be no general process for determining whether a given formula A of the functional calculus is provable. That was the result. Computability has changed since then. It has received a broader interpretation. I have asked a bit around and indirectly got this message from Martin Davis. By the way, there is a new book of Martin Davis on Turing machines that I still have to read thoroughly. At some time in the last 1940s, Post remarked to me that the circle-free problem, this endlessly running machine, was unsuitable for a basis of other unsolvability proofs because, as formulated, it was an unnecessarily high degree of unsolvability. So that is why nowadays we are talking about halting computing machines. In Turing's area, the computing numbers was not halting, but the decision whether the description of a Turing machine could clearly be a halting problem. Okay, now we go to the next step, because I said something about materialization of universal Turing machine. What is a universal Turing machine? It's a Turing machine that hosts a guest machine. I'm using terminology we have nowadays from virtual machines. On your computer, you could have under your Linux system a Windows system or something else, and one is the host and one is the guest. The guest TM, that is the Turing machine that has to be simulated, is encoded. Its description number is written off a tape. Any arguments are added, and then the host TM processes the host. Now, I hope, yes, it's enough what we can see. So here have we a Turing machine. Here have we the number of the Turing machine encoded in something that we want to simulate, and here have we the arguments, and now the machine always goes to the description, does something here, goes back to the description, does something here, and so on. And then by this way we can simulate any Turing machine with one single Turing machine here. And the question will be, how small can we make this one? Now I come to Hasenjäger. Hasenjäger had some comments very late, 20 years after he has built these machines. One was this one. Even though Konrad Zuse had built quite usable computers in Germany, we wanted to pursue the idea of constructing a theoretical Turing machine out of our material. For our purposes, second-hand relays were much cheaper. So it was a challenge to find out what can we do with Turing machines with absolutely cheap material that costs nothing. No budget for that. So it's like a no-budget film, what he's done. This is the machine that you see downstairs, if you go there. I will now show you some pictures of the machine, and partially pictures you cannot see if you go downstairs. So it's good for you that you're here upstairs. You see here the various ingredients. These are 5 boxes. Up in the middle is the 4-state universal machine. That is the state machine. And we have 3 tapes here instead of 1. I will comment this later on. In the front is a result tape, as I call it. If you look at the, if it clear, you see there is an R for Rechenband, which means in German calculating tape. It is the tape for the machine to be emulated. Then we have the program tape, and where the universal Turing machine is, not the universal, the Turing machine that has to be executed is coded, and an auxiliary tape, which I will not describe in too much detail. Here you see a front view removed, even the plastic in front of it, and you see these are exactly 16 relays. That was very funny for me, because when I saw the machine in this situation in Hasenjäger's flat, then I said, okay, it seems to be fairly complete. I take this and start analyzing with it. And then I saw 16 relays. We need at least two relays. And this is clever relay programming for a flip-flop. So we cannot make more than 8 bits out of it, and even that is difficult. And I had a look in the literature, and I found out Turing machines with only 8 states that didn't exist. So this universal Turing machine, so this couldn't be a universal Turing machine. Well, some more. This is the back view. You see the state transition table is directly wired into this machine, and you can even have a bit more look. Now my task was to follow all these wires and to find out where which one goes. And there you see a Turing tape, nicely but not really working thing. He uses halved 35mm photofilms, so he has continuous sprocket holes here, and with this one he makes here notches into the film, and with that lever he senses whether there's a notch, and here we can see it is something to transport in. This was the result Turing tape. It is, as you see, one you cannot erase, but I will not go deep further in that, because it is everybody agrees that it is possible to transfer an ordinary Turing machine into this type. What is also a very interesting device is a so-called selector switch, Drehwähler in German. This arm is moved magnetically from one point to the next point. So we can, let's say, enumerate a number of, or scan a number of positions. This is needed for the program. We have exactly 18 bits for program. This is the programming for the Turing machine. And this is another problem. I found an article of Moore, who had 18 states. That is not possible with 16 relays. And when he uses these programs are very, very long, exceeding much more the capacity of these 14 bits, 18 bits. Okay, but nevertheless, the interesting thing is, can we make a program, a Turing machine, universal Turing machine, so that if we can expand this a bit, we can simulate other Turing machines. This is the circuit semantics, not for you to really to lead, but to impress you with my work. And this, now I will going to say why we have more than one tape. You remember this picture with the head just going to and fro between the description and the arguments. And what is more logical than splitting it up? So you put the program on one tape and the simulated tape on the other one, and so you have saved a lot of effort and a lot of runtime. His Turing machine that you see downstairs is obviously, no, not only obviously, he has written it himself, based on 2 sources. One is an article of Moore, the famous Moore with Moore law, as far as I know. A simplified universal Turing machine. The first article that took up this challenge to make a real describe a Turing machine that could be built. He writes it himself at the end of the article. But as I said, it has 18 states and a very complicated encoding. The other one is an article by Wang. I think he was in Cambridge, but I'm not sure. 4 years later, a variant of Turing's theory of computing machines. Well, the machine of Moore had 3 tapes. You see why now. One tape for the guest machine, a cyclic read-only tape that contains the encoded guest table, the program tape, and an auxiliary tape to store the state, exactly as Hasenjäger's machine too. He had only 13 states at the expense of multiple tapes, as he wrote, and he used a non-erasable Turing tape for the guest, and he cited Shannon that there would be equivalence, but this Shannon proof has obviously never been published. Wang used something very different. Encoding. He didn't use a state machine, he used instructions, like computer instructions. The first one here are the cells where it is, and the first one, write a mark, go to right, continue to location 2 if there is a mark on the tape, the so-called conditional jump, and then left or right. In this case, it means it's the end of the program. To prove that this machine can simulate and can compute any function, has full power of computability, the program is encoded as a product of powers of primes. That is something that is beyond anything to be built with post relays. You do a factorization of these numbers during at each step. So it's an extremely inefficient solution. But this idea of using a program instead of state tables proved as very valuable. So he combined Moore with Wang, the 3 tapes, the cyclic tape, the instructions. We got hints from 2 publications about that, but no concise description. So we had to re-engineer the hardware. Now the question, is this machine down there universal? Well, the simplest answer is if Wang's article is correct, and we should assume that because it exists so long, although it's very hard to verify. If Wang's solution is universal, so is Hasenjäger's, because it's using practically the same instructions. And I have to mention, but for the question, is the machine downstairs universal? I can say as it is not, because there's a bug in it. It is not serious, but we are not going to change the original artifact. So we are, if it is interesting enough, we can make a replica of this. This is not a real problem, but I think it's not so interesting, but this could be then discussed somewhere else. I will just give an example for the machine downstairs that without this bug I could use it, but with this it won't. This one means skip one instruction if there is a marker in, otherwise go R. Because it is cyclic, this skip one instruction simply stays where it is when there is a mark on the tape. Otherwise, it goes right. So this means it finds the next blank space after a series of marks. No, it skips blank spaces until it finds a mark. This is a bit more complicated program. This was 6 bits. This is 14 bits. If you encode this, this adds a mark and the add of the change of marks. It says if there is a mark, skip 2 instructions, go right. Now it is cyclic. You come to the beginning again, skip 2 instructions as if there is a mark. Once there is no mark, write a mark, and then skip 3 instructions. That means it's effectively a halt statement. So this small instruction, and this 14 bits fit into the 18 bits that we have downstairs. So this would be a program that would do it. Obviously, we cannot encode a real Turing machine on this machine there, but it is not so far beyond. Well, this small program of 13 bits does exactly what I showed you with this state table. And you remember the large number of 16 decimal digits that I used to encode this machine. 16 decimal digits of, well, these are much more than 14 bits. So you see why he succeeded in using Wang's method of using instructions to make it smaller. We have this nowadays also, or it had been found out that other encodings have the same effect also. That is string rewriting systems. Here for your information is the state table of this universal machine, because it has only 4 states. It cannot be so large. It is a bit larger because we can see here from state 1, if on tape P is a 1, tape Q is ignored, on Q is a 0, then advance tape P, do nothing on Q, mark R, and next state. For my better readability, I just put a dot here to say stay in the same state. And this is exactly, this is the state table here, on the left, clearly. The right one is only comments to understand. And this is the state table of the machine downstairs that can do all this. This has, oh yes, it still fits, 4 states, and it has the equivalence from my measure of 12 symbols. So the size in my in what I call a TM index is 48. What does this mean? Well, in 1956, Shannon had an article on a universal Turing machine with 2 internal states. And in his article, he wrote, "It is shown how to simulate any Turing machine with one whose state machine has only 2 states." An interesting unsolved problem is to find the minimum possible state symbol product for a universal Turing machine. This triggered many people to find small Turing machines for a certain time. And we had had a workshop these days here in the INI to find out something similar to Shannon's state symbol product, because it doesn't work if I have more tapes. Then I cannot simply use the state symbol product. It doesn't say anything, because I will give you one reason. You can replace any Turing machine with n states and 1 tape with another Turing machine with 2 tapes, provided that you can record the states on the second tape. So it doesn't help you really. So to compare Hasenjäger's machine, you know, remember what I said. When I first detected it, I thought it looks like a universal machine because it is has a fixed program. When I looked at the number of states, I said that cannot be possible, because Hasenjäger would have published it when it was such an advance. But nowadays, I'm sure that it is really an interesting thing. Now we have used our TM index for categorizing several machines. This is a time, here linear, and this is the index. This is equivalent to the state symbol product of Shannon for normal Turing machines. And you see, this was a Moore's machine, and this is logarithmic, otherwise it would have been up there. 10 years later, Hasenjäger had a much better machine. The Wang machine cannot be presented here because he lastly only gives the instructions to do that and not a real state table for that. Then 10 years later, Hooper, we do not have all machines here, just a selection to show you the process. Hooper had 2 other machines. One was a 1-state machine, but 4 tapes, and these index evaluates to 49 then for that machine. And he had another machine with 2 states, but which evaluates to 28. So the smaller, if we go down, the smaller the better. Then we have Rogozin with 24, and long time nothing, because this was finally Neary and Woods gave another solution. So it looks like this seems to be the limit, unless we find a better encoding. So, in the beginning I asked the question, was this just for fun or was this science? Well, the machines, as Hasenjäger said himself, were built for no proper use. He just wanted to play with it. It was hobby for him. It was taken as a challenge. Is it possible to boil down the theory so that we have something actually working? So the question now is, does this help you in developing your theory? And he wrote, the bottleneck was the materialization of a Turing tape. You saw this machine erasing there. It is not so easy to build. And this initiated research in Münster from Hasenjäger and Redding in particular on Turing machines with non-erasable, that's what we have, even non-writable tapes. That is possible if you have a tape with a mark. Then you can go to the left, go to the right again, and then you know you can store a number in it just by moving away from the single mark. Then you can read the number out again by moving back. This is, by the way, what the third tape of Hasenjäger does. Whenever you have to jump, you have to remember how far to jump. He puts this number into this. This is equivalent to a tape with just a fixed mark. It is not writable, but you can use it. And this came to an end to which was called by some people register machines, other people call them Minsky machines, where you only have numbers, have counters. And so it made some research in this area. Unfortunately for us, only some details were published 20 years later, so a lot of information is lost on what he did. By the way, they wanted to publish it, and then was an article from Minsky, and they looked at it and say, oh shit, they're doing exactly what we wanted to publish. And as he wrote 20 years later, he said, we should have read the article in detail. We would have found out that we did something else. So read articles in detail. It is. Yeah. Now I can present you something a few people have seen. That is the machine in working. The machine works, and before it went here, I made just to be sure to have at least one film of it, a film in not such a good quality, but you see the machine working, you see the arrays, you see the tapes. Well, the sound is much more heavy now, would have been much more heavy. Now you see the state numbers here, you see the state is shown and what state the machine is. And this is was by the way the timing, and here you see it tries to punch a tape that is not there because this thing doesn't work. Here you see the selector switch is going around, and here this is the tape that counts, and this is what I wanted to show you. And now you can ask a question if you want to. Thank you for your.
Other questions?
One simple one.
Yeah.
What's the dates of that machine? Do you know
Oh,
exactly?
excuse me. No, we don't know the exact date. We estimated about 1960. We don't know the exact date. And all the time that we had in between, we didn't find it out.
Does his wife not know?
He-
Does his wife not know?
His wife lives, yes, but he doesn't know when he has finished this machine. Maybe one of the, if you find one of the students there. He used, by the way, this machine in his lectures and let it run, and in just this way with a program that we were found on it. You remember? I will just try if I find it here. Yeah, this is the original inscription that we found, but it doesn't say nothing because someone could have. The machine was 40 years, at least, no, 60, yeah, at least 40 years it stood around there, nobody cared for it, and so somebody might pass around and just flip a switch. By the way, it does something useful, it does punch 2
marks and then sequence of marks and marks and living spaces. But I have the impression that from my simulator that nearly any bit combination does something. By the way, this is in any case this is anyhow, so that at a certain point it starts an instruction here and continues it there. So you have that what every computer programmer fears, that you have instructions that overlap. That's exactly what he's using here. Yes?
Was Hasenjäger aware of the bug? Trying to fix it?
We don't know. My guess is yes, he was, because there was a later machine, a larger machine, and because one of the students former students for him now is a professor, he said, well, he just used it for producing bit strings. So it may be that he took it to the lecture and said, okay, this might be a universal Turing machine. It has the potential of a Turing machine. I'm using it just for producing bit strings or something like that. And you know, it is not so easy, I can tell you. I can tell you exactly what to do. Here is a relay with an extra contact here somewhere. And you have to take away the soldering of about 6, 12, 20 wires to take the relay out, find the correct contact and put it in again. And there's a lot of work. And I think because it was for no proper use, as he said, and I think he already saw that these bit number is not sufficient to do something earnest on it. It wouldn't be a problem to make a rebuild with a larger bit numbers. I have selector switches with 32 or something like that, but not yet found a very appealing program for that. Appealing at least for the general public. You know, we are a museum, and then we have to something to appeal for pupils and our schools and so on. But nevertheless, that would be possible. But I think he was aware of that spark and did just moved his attention to some other field. Yeah.
So there's two programs, right? There's the program in hardware that you miraculously figured out what it is, and then there's the program of the simulated machine shown here. So for the program in hardware that you figured out what it was, could you say in a few sentences how you would figure out one of those instructions? What did you have to do to figure out one, for example?
Okay, I could start.
Just in a few sentences.
Yeah. Here you have the schematics. If you are somewhat trained in relays, you see that this is a clock generator. So
did you get these? Did you draw this? Or did
yes.
You,
yes.
Yeah. Well, that's a big
I
thing,
followed
right?
all the wires. I knew how. I found out which relays were it.
Okay.
I made relays model for this schematic system.
Okay.
I put them in the same order for my own convenience. Normally you would move it more logically, but I didn't know what the logic was, so I put it in just the order. Then I saw that this looks like a clock generator, because here is an electrolytic condenser that delays this relay. So this is the clock that is generated, tuck, 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 tuck. Okay, we can set this aside. Now, if we have a look here, we can see, I want to tell you now, that each two pairs here, and you see it from the inscription, I'll tell you very soon, that these two relays always build a flip-flop. So we have 1, 2, 3, 4, 5, 6 flip-flops. Once you know that, you have a more deeper look, you say, two of these flip-flops build a pair of a master-slave flip-flop. Whenever you have a sequential circuit, you have to have effectively two phases, because you must inhibit that the state immediately goes round. So that's why he uses master-slave flip-flops, and then with these flip-flops he stores the state of the tapes, and that with 3 tapes is a problem. So he used alternately one or the two. And once you have that, then you start finding out what make a contact tree. I should be able to show it to you, but you find out which contacts are connected to how. By the way, I simply extracted from the schematic program the information so that I had it easier to write it down. And then from the contact tree, you make a first thing like this state table. Don't know where we have this one. Yes, this one. But this is the final phase. I think I had 4 transformations in between, rewriting the contact trees to state tables. And the funny thing was, because of the error, it looked impossible. There was a transition that led to nothing. And then you think, okay, you must have done something wrong. You look for all the wires, at least that are relevant, look at the contact trees. That's the way it is.
Congratulations.
So this is the table which comes out from your work by reverse engineering the machine?
Yes, yes. This exactly describes what is done to interpret the commands. I don't have the coding now shown, but I could do it. And it says when you are in state 1, we have a 1 in tape P. You see, here in state 1, you never can read Q, and in state 3. And in state 2 and 4, you can never read the tape R. That's why he needed only 2 relays to capture the input from the tapes. And then you can do something on the tapes and eventually change the state of the machine. And here you see the commands. You see if there is a mark instruction, then punch. If it is not marked, just ignore it. This is a funny thing, by the way. I have a theory for it, but I can't ask Hasenjäger any longer. Because of the unreliability, he uses several mark instructions after each other in the hope that one of them would do it. Then, by the way, he does one trick. That's why I came to the TM index. In this state, he uses the tape Q as an extension of the state space. I mentioned that you can move a state to a tape if you have an extra tape. This example where you can change from many states to a one-state machine, that Hooper showed very clearly. And he uses this trick, and if I use this trick further on, I could even reduce, I could even remove the 4th state. So I get a 3-state universal Turing machine. From the engineering point of view, that doesn't help, because I need the number of relays is not lower. But from the theoretical point of view, it means that I have a Turing machine with less states.
What about the symbols in that case? Do you have more symbols?
No. This is just a judicious use that you use. Well, the tape Q is in a certain sense here
So
not yet
will give
used.
you an index of 36 then? Is that what you're saying?
What?
Will that give you an index of 36?
Yeah, it would receive a lower index. Yeah, clearly, because the rest of the machine is equally. It's the same. Yeah, 36. You're completely right.
Once I was in Münster on a conference, and they showed us a whole collection of such machines. So
Yes,
this
that was
just one of them.
Turing norm. Yeah, we still have. I think we now have the collection.
How many are there?
A lot. Well, it's difficult to say. I could show you if you are interested on. I can.
Are they all from Münster, or you collect everything that people?
So they are some, especially this one, is from Hasenjäger. The rest is from Münster, because the widow from Professor Redding, also Professor Redding, she is professor for he has a PhD of 2 faculties. She has collected that, and she has given it to us now. Now it has been archived and numbered by me, and I have work, I think, for the next several years. If you are interested, I can show you what we have there. The difficulty is to find which belongs to what, because it has simply been stored somewhere.
But it's not in Munster anymore, it's in the
No,
Heinz
no,
Nixdorf.
now it's in Paderborn. So everything that we thought was that we could get is in Paderborn.
So, do you believe that the machine you have here is the oldest one, the first one?
I believe yes, but I'm not completely sure. I have to ask his son for this once again. His son still lives, and he's very interested that we conserve these things and so on.
And are you aware of any older attempts to build a physical Turing machine, or is this really the first one?
I think it is the first one, but well, let's say, by searching the literature for information about small Turing machines, I didn't find any hint except that Moore in his article says, well, this machine is so small, I think we can build it. Yeah, but I don't know whether someone did it. I didn't find anything. Didn't find more questions.
Then let's think what we do.